random matrices. So also to my colleagues, so in Krakow, they regularly run a workshop, and the workshop posters always looks like the poster advertisement for the movie Matrix. So it's these columns of rows.
Alright, yeah, I really told me. No! But
So
what about the infinite version of that? Infinite random matrix, the movie is infinite, so you're always watching.
Okay. So let me add a piece to that movie. Okay, so here's a short recap where we are at the moment. So we have restarted our efforts in trying to solve random matrices now exactly at finite n. So here's the partition function. This is for beta equals 2. And we just learned about some very nice trick in rewriting the one-number determinant, which is just a matrix. It's a determinant of a matrix where you just have powers of the eigenvalues, and by adding columns starting with the very right one from the left to the right with arbitrary coefficients, you can generate arbitrary polynomials here of degree n-1, n-2 up to degree 0 in this determinant without changing it. And now picking these polynomials such that they are orthogonal with respect to the weight function, which is in the simplest example e to the minus lambda I square on the entire real line, or for one of the other 10 classes, well, this is beta equals 2, so not all 10 are included here, but you remember there was some lambda to some power alpha times e to the minus lambda for the Gaussian ensembles. But this is very general. I mean, this can be non-Gaussian, like quartic potential we had. So this first thing we did calculate was the normalization constant, just doing some tricks, expanding Laplace expanding this determinant, and we found that up to constant that we will drop anyway in computing densities. This is given by the product of the norms, or the squared norms of these polynomials. So because these polynomials seem to be very useful, it's a good idea to study properties of these polynomials. Of orthogonal polynomials, or OP, short for orthogonal polynomials. So one property is a recursion relation. And that goes as follows. So you will all agree that if the polynomials form kind of complete set of functions or of polynomials, then multiplying the polynomial of degree k should be expressible in terms of all polynomials of degree up to k plus 1. And of course, if these are monics, then the leading power is lambda to the k, so the leading power will be lambda to the k plus 1 here, so the coefficient is 1. Okay. Now, what turns out to be true is that this expression here is just a 3-step recurrence, and that is true for any set of orthogonal polynomials on the real line, also Chebyshev or polynomials on, let's say, 0, 1. They all satisfy this 3-step recurrence relation. Okay, now how can we prove that? This is very simple. So we just write that k lambda k as some linear combination from 0 to k plus 1. Let's call them ck. I have too many k's here, so cl that became k, and then we have pl. Okay, so this is just an expansion. Okay, in scripts I call this alpha, so that's consistent. And then these alphas you can just project out by multiplying this by, let's say, pk prime, and then use the orthogonality, and then you will just get a delta lambda k prime. Okay, so that implies that alpha is pk, and then of course you don't get data, but you have to normalize with the norms. So you just get the following expression: lambda pk p. Okay. So nothing fancy has happened. Now, lambda is just multiplication, so rather than multiplying this guy, you can also multiply this guy. And now you see, lambda times this will be a polynomial of degree L plus 1. Now, pk is orthogonal on all polynomials except on k. So, if L is less than k minus 1, you get a polynomial of degree k minus 1, and that is clearly 0. So from that you can conclude that you only have these 3 steps here. Now we can also express these coefficients here through so ak and bk can be expressed through the norms and also through the second coefficient. But I will not do that. I would rather give you an example which is instructive. So the wave function is just Gauss. Then we have already seen that the polynomials are Hermite. And then you can in fact compute the norms. So the norms are just in the tutorial. And you can also compute these coefficients here. Now, you can see, first of all, that this middle coefficient is 0 because well, the middle coefficient you would get when you project here on the set that. So alpha k is ak, and alpha k minus 1 k. So the coefficient in the middle, well, you just get lambda pk squared. Now, Hermite polynomials have parity. This has parity, so you integrate over something of odd parity over the full real line. So that gives 0. So that's why k is 0. And clearly, polynomial is even. You multiply it with lambda, you get something odd, so you should only get something odd here. And that is true for all wave functions which have parity. So also for our quartic or sextic potential. And then the bk, well, that will come in a moment. Of course, I would like to now move to orthogonal polynomials. Oh, okay, this is very trivial. You just normalize them by the norm. Write that down nevertheless. hk L. So obviously then the p's are also normal, so we don't have this anymore. We divide it by that, and the recursion then simplifies or it becomes more symmetric, where okay. Okay, maybe I should have called this slightly different here. Plus ck minus 1. So this ck is the square root of hk over hk minus 1, if I'm not mistaken, yes. And the ak doesn't change, just the normalization is simpler than number Okay, this is an easy exercise where, I mean, it's clear you normalize by the square root of hk. You divide this by square root of hk, then you add square root of hk plus 1, and you divide so that it's normal. So then you get the first coefficient, and the fact that this coefficient is exactly like this one, just shifted by 1, this is an easy exercise to do. Okay, why did I introduce these orthonormal polynomials? Because they will lead to the kernel of orthogonal polynomials, and that's defined as follows. So it's the sum over this bilinear of polynomials of degree L from 0 to n minus 1. This is just convention, depending on x and y. Now, why do I introduce this kernel? Because basically all correlation functions, so all densities, can be expressed as a determinant of this kernel. So if you like, this is like the 2-point function building block, and we will show that this is actually a 2-point function of some kind. That from that everything will follow. Okay? Now, in order to prove that, I need some properties, and they are called contraction Markov properties. And these contractions hold for any kernel that satisfies for any kernel that satisfies these contractions. We will prove some theory now here. For this kernel, this is very easy to show. Kn lambda equal to n. This is very simple. You just integrate this. Every integral for equal arguments gives a delta LL, so 1, and you sum over n terms, so you get n. And as you will see later, the density is actually this object. Okay, and that's why it's normalized. Then you can also see the following property. I said contraction, so we better want to contract something. So knx lambda kn lambda y, this gives kn of x and y. Okay, so you integrate over 2 kernels which have one argument in common. Now this is again simple. You multiply these 2 kernels, so you get a double sum, and then you pick the second one, PL, let's say, multiplied with the first one, let's say PK, you get a delta KL, which is one of the sums, and the kernel will remain. And note for this, it's of course important that these kernels are also normal, because otherwise you would get some factor, and then you would get a sum over a factor of some kernel, and that would not be the same kernel. Okay, and the last property that is also trivial to see is we don't really need that, I think, of kn of lambda x, let's say this is 1. So you integrate over a kernel where you just have one argument that you integrate over, where you plug it in here, then you only get something when the degree is 0, because this is Pn of x. Pn of x is something constant, so it's proportional to the zeroth polynomial in lambda. And that's why you only get a contribution from that first order term. Okay, so these are the properties that our kernel has. And we can use them in the following. Now there's one more thing that I would like to show for this kernel. Now, even though we are now in the position with all these tools to solve matrix models at finite n, eventually we want to take the larger limit, because only in the larger limit we expect something universal to happen. And so I will show you that this kernel is a very easy asymptotics because of the following. So there's something called Christoffel-Darboux identity. So what is that? That means that, first of all, and this is really the Christoffel-Darboux identity, Kn of x and y, well, this is equal to Cn, where this Cn is Ce. So from now on, Cn will be something specific, times Pn of x, Pn minus 1 of y, minus arguments exchanged, Pn minus 1 of x, and x minus y. Okay, now you immediately see that if you Taylor expand this Kn x in x, and then we don't make a mistake, Cn of Pn prime of x, Pn minus 1 of x minus Pn of x, Pn minus 1 of x. Okay, so this is the Christoffel-Darboux identity. And what you see from that is if we, I said all correlation functions will be written in terms of this kernel. And then, of course, if we have to take the larger limit, we have to assess the limit of this kernel. And you see all we will have to know is the asymptotic of the polynomial Pn and Pn minus 1. If that works out. So I think this is trivial from using Taylor expansion. So let me just show the first line that is also simple, namely just the following. You take the kernel as it is defined and multiply it with x minus 1. So what do you get? X.
Sorry?
Yes?
Pn of 0 is 0?
No, it's 1.
It's 1.
Sorry, Pn of 0 is a constant.
Constant. Okay.
Because you remember in the Vandermonde determinant, we added all constants, all powers to the polynomial, and there's no reason in general why P of 0 should be 0.
Okay.
That will only be true in special examples. For example, for the Hermite polynomials, the odd polynomials will be 0 at 0 because they have parity, but the even ones will be constants. Okay. Yes, we wanted to prove this identity, Pl of y minus Pl of x, y, Pl of y. Okay. Now you put in this three-step recurrence, namely in this form, normal. And then you see that you get here Pl plus 1, Pl, now the ones where the degree doesn't change immediately cancel, right? You see that the ones where we stay at the level Pl, this gives 0. So we only have contributions when this goes up to n plus 1 and down to n minus 1. And likewise here. Now, you can easily convince yourself that this will be a telescopic sum, and the only term that we do not cancel from here is the one where we have degree p n plus pn, so from n minus 1 we go to n of x, because there's no pn of x here. And the other one that we don't cancel, this telescope sum, is when here index is n minus 1, so you get pn minus 1 of y. Okay, and that is what you see here, and then the coefficient should be, if I didn't make a mistake here, the coefficient, yes, so this is the last term in the sum from here, and this is the last term in the sum. Okay, so it's a telescope. Okay, I think you can see that more or less. Now there's one consequence of this Christoffel-Darboux identity, maybe the first one here, and that is that we can write the kernel as a determinant itself. So Kn x y is n of x. divided by x minus y. Okay. So this is nice because the structure to have something that's written as a determinant divided by a Vandermonde. This is a Vandermonde of size 2 by 2. This will come quite frequently. Okay. Now, before I can prove that all correlation functions are expressible through this kernel, I would like to point out two representations of these polynomials. Because you would say, aha, I mean, of course, I've chosen them to be orthogonal with respect to their weight, but other than Gram-Schmidt or the recursion, how do I get them in general? Now, here's an identity. So, it's a relation of pk and kn for averages of characteristic polynomials. So for p we will need one det, and for k we need two dets. Okay? And that looks already almost like a partition function of fermions, right? And that will be useful later. So the first identity is the following. So this is an expectation value with respect to the partition function that I've written down for you, and the size of the matrix is n.
Sorry,
Yes. Determinant of x minus
okay.
h. So, oh, sorry. Yes, thank you. So this can be written, of course, as follows. So we now drop all the constants. K from 0 to n minus 1 hk. Integral lambda I omega lambda I x minus lambda I times Vandermonde. Okay, this is just a definition. Okay, so this comes from diagonalizing h, and then the determinant is just a product of the diagonal terms. Now, this equation is called eine formula. And this is actually from the 19th century. You cannot, maybe you're not surprised because orthogonal polynomials are an old topic. Now, the second identity is much more recent, as you will see. That comes from the 90s. So, what is that? Well, we have an arbitrary weight function. And that means for arbitrary weights, we have an n-fold integral representation. For orthogonal polynomials with respect to an arbitrary weight. Okay, you may say when n becomes large, this is maybe messy, but this is what it is. I mean, it's very general. Now let's do a first check. I'm sorry, this should be a mnemonic polynomial. Otherwise, our check would fail immediately because the check is if the limit x to be very large. So then, well, the leading power here will be x to the n times expectation value of 1. So that x to the n plus the dot, and that at least agrees with the left-hand side of the leading order. So the identity that we have here is not totally stupid. Also, this is a polynomial of degree n, as you can see here. Now, how do we prove that? Well, we prove that in the same way as we computed the partition function, using one particular trick that is very useful. And the trick is to absorb this product here into one of the Vandermondes. Okay, so And then we have the Vandermonde determinant, and you remember this was the following object, lambda j minus lambda k. Okay, so this is an order product, so the sign, so that we really get a determinant of ones, etc., is that the lambda with a larger index is over to the left. So if we call this here lambda n plus 1, you see we get the product of lambda n plus 1 minus all the other lower lambdas. So this is in fact the Vandermonde determinant of degree n plus 1. Okay? That's a trick that is very often useful. So let's now compute this thing here. So we can continue to write this. So now what we have is we have the Vandermonde of degree n plus 1 times the Vandermonde of degree n. Okay? Now we expand both Laplace expansion and use orthogonality. Yeah, that is all we need to do. Times. Okay, so let me write down the expansion. Again, we have permutations. 1 over the permutation group of size n plus 1. That's this one. And then 1 Vandermonde where we have permutations of n there. Okay, so basically, you know the trick already, it will come. 1 minus 1. Now, remember, we still have to tilde this because the Laplace, the Vandermonde is replaced by monic polynomial p sigma n minus 1 lambda n. And then we have the term p sigma n plus 1 minus 1 lambda n plus 1. Then we write this again as x. Okay, and then we have here times p sigma prime 1 minus 1 lambda 1 p times sigma prime n minus 1 lambda n. So see, obviously, I mean, one of the products has one more term because the Vandermonde determinant is one side bigger. Okay. So now we do the integrations. We first integrate over lambda 1, and so on and so forth. Now we have to be careful because we have to see what happens here. And to see what happens, let us look at the index of the polynomial that is not integrated over. Okay, so this polynomial that depends on x. X is the argument of our determinant. So this is not integrated over. This will have a certain index. Okay? And we run over all these permutations. Now suppose it has an index that runs between 0 and n minus 1. That means that one of these cannot have that index. Okay? But if one of these does not have this index, the index is missing, does not have its matching partner. Okay? So that will give a delta 0. So the only contribution we get is when this index is the highest one, because then all the others can match up. Okay. So what do we get? We get from here get sum over permutations sigma 1 n minus 1 h sigma j minus 1 times p now degree n of x. Okay. Now again, this you can reorder. Every term appears once, so this will cancel this one, and then the sum of permutations will give an n factorial, which will cancel this one, and then this is the answer. Okay, this is the proof. Now, I would like to make a comment here. I came up with these Hermite polynomials as an example. I think there's a coefficient here which I forgot. Let's else. Now, if you know orthogonal polynomials well, you know that they have many more properties, not only three-step recurrence, they have a Rodriguez formula that you can generate them by differentiation. And typically they also have a single integral representation. These are the classical orthogonal polynomials. So in this case, the integral representation looks as follows. I hope this is correct. And that, of course, should be equal to some p. So what you realize is that this single integral representation with something to the power n is equal to an n-fold integral with something for the determinant to the power 1. Okay, so this is a kind of duality relation. So integral to the power n of that is integral to the power 1 of that to the power n. And this can be shown explicitly whenever you have a Gaussian wave function here, so not only for Hermite but also for Lagrange, using what I have mentioned already once, which is something that's called supersymmetry. So you write the determinant as an integral over Grassmann variables, then you do the Gaussian average, do Hubbard-Satonovich, and then your Hubbard-Satonovich variables that you get is this one. Now, why do I mention this? I mention this because in this form, this is of course much better to do saddle point approximation, because at the end of the day, we want to know what is the Lagrange behavior of the polynomials to be stuck in here. Okay. Now, of course, for the classical orthogonal polynomials, you may find all the other topics done in books, but nevertheless, it's good to know that this is nice for saddle point rocks. Okay. Now there's a second formula I would like to show, which is true for the kernel. So let's write that down. In fact, I have to say that this field of orthogonal polynomials has, of course, always been an active and interesting field in mathematics, but the relation to random matrices has really pushed this forward, and many people have now worked on asymptotic analysis of the polynomials that appear for general weight functions in these matrix models, and they have developed techniques, for example, matrix Riemann-Hilbert problems, and solve them to rigorously prove universality for this kind of setup. Okay, so this first relation was this one. The second relation is this one. Okay, let me put factor h on the left. And the n we have here is n, and here we have n plus 1 actually. Okay, so again we can check. I mean, I erased the kernel, but you remember the kernel now with n plus 1 that has the highest polynomials of degree n, and the leading power of them will of course be x to the n, y to the n, divided by the norms, because they are also normals, so divided by hn, that's cancelled this one, and that scales exactly like this when x and y become large. So this will go like x, y, n. So at least the leading order term matches. Now the proof goes actually the same way as here. So maybe I don't have to explain that in detail. So I mean, so this here will give 1 to n x minus 1 of I, y minus 1 of I. Okay, just by diagonalizing. And then in the partition function, we also have to multiply this by Vandermonde square. So let's take one of the Vandermondes and stick this in, and take the other Vandermonde and stick that in. Okay. Then the next step is to do an expansion like here. And so what we will get is we will get the same thing almost. Right.
Sorry.
Yes.
So you
Yes.
have another integral like in the other case, but with just x minus lambda a and I and x on minus lambda I, right?
Yes. So I just write this in this fashion.
Yeah.
Shall I write it out again, or is it clear? I mean.
Okay.
So we just diagonalize the two determinants. That gives this product times this, so the product really not runs over. So that is like this. Okay, and then this I have to stick into the partition function. Okay, this is the partition function. I just have to stick in these two products. Okay, and then the trick is now we have two products and we have two Vandermondes. So on each of the Vandermonde we stick one of the products. So this will give a Vandermonde of size lambda n plus 1. And this will give another Vandermonde of size n plus 1, but the largest eigen, well, the largest, I mean, the eigenvalue is the largest label. Here is x, and here is y. Okay? Then I expand these two Vandermondes now, like here. So that's what I've done in a quick way. So this was what we had before, and now the only extra term we get is we get another polynomial that depends on number 1. Okay? And now both commutations run over n plus 1 variables. Now we have to integrate it over n variables. However, our previous argument that this here has to be the largest does not work anymore. However, what does work is that the index of the two unintegrated polynomials has to match. Because if this doesn't match, then we have here something that doesn't match with here. Okay? So what we get is we get the sum of our possibilities for indices for these unintegrated polynomials, and from the rest we will get deltas. So let me try to write this down. So this is hn1 Okay, so now one sum of permutations is killed, and we have to do the following. So we get this from h sigma, actually let me write it like this, of j minus 1, where this index is yes. So, as I said, the integrated polynomials will stay and they will have the same index. And then the permutations run over all the remaining indices. Okay? And we have so many possibilities. So the index of the unintegrated polynomials can be 0, 1, 2, up to n. Okay? That's what I've written here. Sorry, this should come to n. Now, this thing here is almost the complete product of norms. There's just one norm missing. namely the one with index k. So let me add that, not add, multiply that and divide through it. Okay. So now we see here we will get the orthonormal polynomials. Okay. And here we now get the complete product of all norms. So that now we can pull that out of the permutations because it runs over all permutations, which is always the same. So you see that this will cancel that up to Hn, which is nice because that's already here on the left hand side. Coming from here. And the rest, let me write this down. Here not to lose the line, so we will get Hn over n factorial. Then we have the sum over permutations. So these are only n indices. Okay, because one of them is fixed. And then we have the sum over k from 0 to n, pk x, pk y, without tilde. Okay, now this will cancel the n factorial, and this times this is just the kernel at n plus 1. Okay. Fine. Now you will ask, of course, what if I compute more products of determinants? We will do that later because we will need it. Because basically, now if you would believe that this matrix model has anything to do with field theory, these determinants look like having integrated our fermions. So these come down from Dirac operators, and if we want to have NF flavors, we need NF of these determinants. Okay? Now the thing is, and I will not write down the statement, this product of average of so the average of products of characteristic polynomials, they are also called characteristic polynomials. I should have said that. It's clear when you diagonalize a matrix, you look at the characteristic polynomials such as lambda minus h, and then you find the eigenvalues. So this is why these determinants are carrying this name. Now for product of those, this can also be expressed in terms of the kernel and of the polynomial. So for example, if you have an even product, you can describe this as a determinant over n. I will not prove that, but state that later, and so on. Okay, so now we want to prepare the next step, that is the computation of the density correlation functions. So, now, in order to do that, let me do a few more steps to prepare. So this was, as you remember, the determinant of, maybe I should start. Let's go back. Linear algebra, first year study. Determinant of A square. Now, if A is A transpose, then we can write that. Of course, we can also write this as that A square. Okay. That A transpose. Okay. There's no big deal about this. And we will do that now for our determinant square. So this was the determinant of P of degree A minus 1 over lambda I from 1 to n square. So if I call this matrix A and then take its transpose, then, sorry, this is of course for these polynomials, I can massage this, but before doing that, I would like to normalize these polynomials. So this I can do. Well, as you know, I can multiply things into determinants, into common rows and columns. So if I address this by following product, then because I have this twice, okay. So if I pull this out of the determinant, I get the product of all vector square root, and then I get it squared, and this will cancel. Okay, so I've just multiplied and divided by the same thing. Now, this matrix here I shall indicate for it. And then I will multiply it with A transposed. So I will have A transposed. So if I take Ij here, this is the sum over K from 0 to n-1, Ai K, J, right? Transposed. So if I undo the transpose, I get here J and K, and then I get this is the sum over K, 0 to n-1, P of index lambda I, running over K, running over K, okay? Just simple linear algebra. So what we have shown now is the following, that the Vandermonde determinant square is equal to this product that we have anyway in front of our partition equation times the determinant of Kn of lambda I lambda J. Okay. Now you will remember that this kernel has nice properties. So for example, when we integrate over two kernels, we get one kernel. So this is the determinant of size n by n. So the joint density, so the integrand of the partition function, is just a determinant. And maybe I should make this statement. So times so our partition function can be written as an integral over a determinant, and such integrals they are called determinants. Point process. And what they describe is always, if you think of the lambdas as particles, these are particles that repel each other, because whenever two arguments agree, the determinant will be 0. So the probability to have lambda i's to be equal is 0. And the way they repel each other is through this determinant. Okay. Now, now we want to compute the following object. Okay, and that is this whole thing here, integrated not over all variables, but only over n minus k. Okay, so and then integrate to plus 1 n times this product. Okay, so now this looks pretty bad because these are n minus k integrals, and this is a determinant of size n by n. So if we want to take n large, we will have to do something. Now, what will come at help is that this property that the integral of k gives k. So what we will show now, there's a theory that shows that integrating out one argument of the determinant will reduce the size of the determinant by 1. If we do that successively, we have n minus k integrals, then this should become a determinant of size k by k. And that is feasible when we take the larger limit, because then the size doesn't change, it doesn't depend on n anymore. Inside the kernel, we have the polynomials. They are gone, but remember the kernel is just depends on p and p n minus 1. So then everything is nice and explicit. It's solved for finite n. We can do it. So this is what we will have to show now. I'm just thinking. So let me write down the theorem, and then we have a break to refresh to prove it. So the theorem that one applies in the data. Was as follows. For k rated kernel, so for example, k x y that satisfies these contraction properties. So these contractions property. So for this is an example for such a kernel. We have that integral dx n over that n by n k of x y xj is equal to constant minus n plus 1. The determinant of size n minus 1 times n minus 1. The same kernel, well, of now the variable xn has gone. Okay, and C is just normalization. Okay, so in our case this was n. So this is the theory by Dyson and Meta. They wrote it down in a slightly more general form, which we will not need. So this is what we have to do, and you see that if we apply this successively, this will simplify already. But I think it's good to have a break. Okay, 5 minutes.
We are ready.
Perfect. So here's our goal. We have a kernel like this one. We want to show that integrating the determinant of such a kernel over one of its variables will reduce the size of the determinant by 1, and the coefficient is this one. So let's look at the determinant and see how we can collect all these terms. So this is the sum of our permutations. X1, X sigma 1, up to K, this. Xn, X sigma. Okay, this is just a definition. Now in this sum of our permutations, we will have n factorial terms. So let's pick first all the terms that have sigma n equal to n. These will be n minus 1 factorial terms, and those we will treat first. So n minus 1 factorial terms with x with sigma of n equals to n. Now for these terms, it's very easy to integrate the kernel, the determinant, so that the integral over such terms, we can pull it through, it will only see this term. This will give a constant c because of this normalization. I mean, I've just put the weight inside the kernel. And then it will give this, but this is just the determinant of size n minus 1 by n minus 1. Okay, it's clear. So this is already what we want. N minus 1, a of x I. So that's really the first part of our theory. Now what about the remaining ones? So all remaining permutations can be reached by doing one pair exchange, so exchanging one of them with any other one here. So, for example, a xj x sigma j. And of course, I will have n minus 1 possibilities to pick the second argument, which will become n. Okay? So I will have n minus 1 possibilities to pick one of these second arguments to be n. So what I do is, so I have first all those where n was here. Those I've dealt with, and now I have to take all the other ones. So I have to make a permutation. The n should appear in the second argument somewhere else. There are n possibilities to pick this position. And and for the integral, I will simply get this. Well, this will just give a contraction. Okay. So I've reduced the number of kernels by 1. And when I do this pair exchange, I get a minus sign. Okay? That is the rule when you do exchanges in permutations. When you do one pair exchange, you get a minus sign. Okay, so I get a minus sign. And then I get n minus 1 such terms. And what remains is now, well, this has been deleted, it's replaced by this. And what is standing there is again the determinant of size n by n, n minus 1 by n minus 1. So I get again this times get kx times xk 1 to n minus 1. So this together with this is this. Okay. This was not so bad. So what we want to do now is we want to apply that to compute these objects here. So basically, we just have to count the right number of coefficients. So and that is not so difficult. So let's do the first of these integrals. Let's say we take this one. In our case, so here we have integral the lambda kn of lambda is n. So this is our c. So for the first integration, we get a factor of c, which is n minus n plus 1. So we get a factor 1. Okay? So okay. So we get divided by let's write this one out. Oh, this I have already cancelled, making this also normal, so this should go. So this Zn, okay, this to be precise here, we should just get, you know what I mean. This will cancel that in solids, okay? So this need anymore, so we have only this left. One integral has gone, we get a factor of 1. Second integral, now our size of the determinant has gone from n to n minus 1. So this n will be n minus 1. So minus minus gives plus. C is the same, so the next factor gives a 2. Okay? We do another integration, this will be n minus 2. We get a factor of 3, etc. So we do that n minus k times, so we get 1 times 2 times n minus k, which cancels this, and what remains is the product 1 to k, because the weights that were not integrated over, they were not used up. All the other weights were used up in this integration. Okay, so k, and then we have the determinant, so comma kn, comma I, comma j, where I and j run from 1 to k. So this is our first big result for arbitrary correlation functions in the matrix model with an arbitrary weight expressed as the k by k determinant of the kernel of orthogonal polynomials. And now we see why this funny normalization was chosen by Mesa, in fact. It is so that this formula has a 1. Okay, that was his choice. And if you like, we could also pull these factors into rows and columns like this, and then put that into here as well. Okay. This is a matter. Maybe it's good to see 2 examples now, and to explain a little bit more notation. So the examples are the following. So density. R1, number 1, this is just a determinant of size 1 by 1, weight function, number, and equal arguments. Okay. Now you see we have a completely different characterization of the density. It's given as the weight, an arbitrary polynomial potential here, times sum of orthonormal polynomials, or using Christophe-Delarue, just as the Pn of lambda times Tn minus 1 prime, etc. Okay, would be written down. Second example, two-point density. Okay, so this is just R and k equals 2, lambda 1, lambda 2. So weight function of first argument, weight function of second argument, and then we have the determinant. Okay, so k and lambda 1, lambda 1, k and lambda 1, lambda 2, k and lambda 2, lambda 1, and then k and lambda 2, lambda 2. Okay, so this is simple. So you see the diagonal dressed with the weights will just give the density at lambda 1 times the density at lambda 2. And the off diagonal, well, in the construction of the kernel, because this is a kernel of real polynomials, the kernel was actually symmetric. So this is equal to that. So we just get here a minus w lambda 1, lambda 2, kernel in one order, let's say, square. Fine. This is what we call connected part. Now we did the resolvent and also the density. So this is, if you like, row connected. Because the factorized part has the subtract. So, but this is all for finite n. Okay. Then maybe one more remark. Very often people pull this weight actually into the sum. So they will have weight of lambda 1 PS lambda 1 square root. And this is of course squared. So these things people sometimes call the weight function. And then the weight functions are also normal without putting anywhere. But this is just, sorry, wave function. Wave function. This is just the name I want to mention. Okay. Now the next question is, of course, this was for beta equals 2. So can we also play this trick for beta equals 1 and 4? Now here I will be a bit more sketchy, but I will at least try to convince you that yes, also these other two symmetry classes can be solved exactly. I will not compute all for you, but give a few steps, and also write down two integral identities that I think are very important. Put them in the back of the mind. So.
So,
Yes.
is there some, I don't know, intuitive picture of how do these correlations behave in simple models when, like, you know, for widely separated eigenvalues?
Yes.
Something
Yes.
like that, just to get a grasp
Yes.
of what's going on.
Sure. This is all for finite n. So the picture that you should have in mind is even your name. So this is just like the semicircle. So this is the density at finite n, which is this thing here. Now you want to know what are correlation functions. So then, okay, I would have to plot in 3D, but I could plot something like R n2 of lambda 1, lambda 2, and then if this definition makes any sense, this should give you something proportional to the probability to find one eigenvalue at lambda 1 and one eigenvalue at lambda 2. Now, if you take this eigenvalues to be at large separation, so let's say one here and one here, then you will have to look at the results that we derived with the loop equations. So, so the leading density was this deformed semicircle with a polynomial in front of the square root. Then I didn't write down the two-point function, but this can be calculated. It's also given by a rational function. This would determine the probability to get one eigenvalue here and one eigenvalue here. Now, if you choose, in contrast, because you asked to have these two eigenvalues very close, then we will get a very different behavior. Then we don't have rational functions that only depend on the endpoints A and D, but then we get, we, so to speak, amplify or zoom in with a microscope into this vicinity. And what then happens is that, well, many things will happen. The first thing that will happen is that, remember, in the larger limit that we took using resolvents or loop equations, we said that this is of leading order, and this will be of the order 1 over n squared. When we do the scaling here, so for example, lambda 1 minus lambda 2 will be of the order 1 over n, so that this is order 1. Then this will no longer be true. Then this term and that term will become of the same order. Okay, so this is a different larger limit, this microscopic limit, and we don't have factorization in this limit. And what comes out if you pick the points to be in what is called the bulk of the spectrum, so you stay away from the edges, then the famous result is that this will go to what is called the sine kernel. Now here's a constant that is not very important, so let's call this here psi 1 and psi 2. Okay, so what becomes the sine kernel is actually not a two-point function, but so the kernel k in 1, 2 will to go to this, and then the two-point function will be the determinant of this kernel. Okay, so the determinant of this kernel is then equal argument, this gives 1. So then this could go to 1, 1, sine. Okay. Now that's not all. There are more larger limits. For example, if you pick both eigenvalues close to the edge, then you don't get this asymptotic. And in fact, you can see this asymptotic already. I mean, I've given you all the hints, so to speak. Let's take Gauss. Then for Gauss, these polynomials are Hamid polynomials. Okay? Hamid polynomials, you know, have a sine and cosine asymptotic. Now we have sum of even and sum of odd polynomials. Okay? Now sine square plus cosine square gives sine minus the arguments. Okay? So you see this comes out. This is the sine kernel that comes out from the Hamid polynomials. Now there's another asymptotic of Hamid polynomials that is less known, and this asymptotic is, by the way, universal for any reasonable confining potentials in the weight. These are rigorous mathematical results, really proof with epsilon and delta and full Monty. People who did this first are co-workers of, first of all, Alexander Hicks, who did some work on that with Pablo Blea, and then there's a group of people around Percy Live from the Coulomb Institute who wrote a series of papers using Riemann-Hilbert techniques. Now, the second limit where you find something interesting is at the edge. So now you will look at something like lambda 1 minus b. I don't remember the scaling. It's a different scaling, so this you will call sine 1. And then the kernel will become what is called the airy kernel. And that is something like this. Airy A function of x. Airy prime of y minus airy 1. Airy prime of x. And that is not all. There's another limit when we look not at GUE but at the chiral ensemble, because in the chiral ensemble, as we will see, or I've already given indications, I think the eigenvalues come in pairs. So each eigenvalue has also its partner minus the eigenvalue. And then the origin is special. And then these, so here will be something happening. So there we will use Laguerre polynomials, and Laguerre polynomials have Bessel functions asymptotic at the origin. And this will give a third class of kernels, which is given by linear Bessel functions. And that is about all. So these are the 3 different universality classes that you can get for the large n limits, I should say, because they are different limits. So these give local behavior of fluctuations.
Which doesn't seem, does it have to do with CFT again? Because it doesn't seem like.
No, this does not have to be CFT. You can make a connection when you go to this limit here where you multi-critical scaling. Okay, then you no longer get Tracy Willem, then you get a multi-critical kernel, and that would have a relation to CFT. Okay. But the sine kernel and Bessel kernel.
I mean, signs appear in CFTs with boundaries into dimensions,
Yes,
but I'm not
yes.
sure it has anything.
I don't think that's a simple relation. Maybe wrong. So these are the special functions that appear in this kind of setting. Okay, so I hope you took this a bit to relax. So now we will attack solve beta equals 1 and 4. So for that, I need other tricks. So let's do first the trick for beta equals 4. Now I will spend less time here, so I will be more sketchy. So remember, in the partition function, we have 1 to the power 4. And one can show that this is actually equal to the following determinant of size 2n by 2n. So 1, 2, so I put here lambda I to the power j minus 1 and j times lambda I to the power j minus 1. Okay, so I could swap that would give a minus sign, but I mean, I hope it's clear what is meant. So I have always, let's say this is lambda 1, lambda 0, then lambda 2, lambda 1, etc. Okay. Now you clearly see that this is the derivative of this. So this is an identity that I will not prove, but you can check that looking maybe at Meta's book. So now we can do the same trick. We can again add columns to each other, and it's clear that when we do that, when we make here and here a polynomial, let's call that q tilde of degree I of degree j and I, and here we get the derivative of q tilde. Okay. Maybe write that prime is primes respectively. So what we will have to do, we will have to find in a way polynomials q, and at the moment there's the monic, such that we can do the integral. Okay, but now you see we have a single determinant of size 2n by 2n. So we will need some different strategy. We need a different scalar product and a different identity. Now, in order to explain that identity, I need some more notation. And the notation is about the Pfäffchen determinant. So what is the Pfäffchen determinant? With Pfäffchen determinant, but typically we define that for matrices that are anti-symmetric and of size n times n and n7. Okay, and then the Pfäffchen determinant is basically taking the square root of the determinant. Okay. Now you may not want to compute the determinant of a matrix of size 2n by 2n and then take the root. I mean, this of course is cumbersome, so there's of course another definition. Okay, there are two definitions that we write on. The simplest one, so it's a sum over permutations now of size n, and they are ordered. That's why there's a factor 1 here. Such that, okay, so there's a sign, and then the difference to the determinant is, in the determinant we always have 1 sigma 1, okay, 2 sigma 2, etc. So that means every index appears twice. Okay, now the Pfäffchen, every index appears once. So sigma 1, sigma 2, sigma 3, sigma 4, etc. And when I say ordered, I mean that I order them that the first index is less than the second one. You can also write the definition without the ordering. That will give some factors, but it's in the notes. So let's give some examples. In the formula I raised here, that will become almost true for beta equals 1 and 4. The difference will be that we do not have a determinant, but we have a Pfäffchen, and we have a kernel that obviously has to be antisymmetric in terms of the polynomials to be chosen. Okay, so let's first do an example. So n equals 2. Pfäffchen of a is just n1, 2. You have two indices, you can only have one permutation where the first index is less than the second. 4. Function of A is. Now, the sign here, this comes on by first taking the identity, and then whenever you swap, you get a sign. Okay? So, A, 1, 3, 2, 4, plus A, 1, 4, A. That's all. 3 terms. Okay. That's your term. So what we will use to tackle eta equals 4 is a very nice integral formula for n-fold integrals. Now there will be 3 integral formulas that I will present, hopefully. So that's one of them, and I think they are very nice and useful. I will only prove the one for eta equals 2, which I haven't presented yet, and the proofs for these formulas that are named after De Bruyne. 1955. You can find in our handbook, approved by Mark Adler in chapter 5. Okay, so what is that? That's an integral over n variables over a determinant of this kind. So 2 different functions here. Of course, both have to be integrable, but they don't have to be derivatives with respect to each other. This formula here is more general. So define inside. And what we get is the following. And now we get something. We have to get an antisymmetric matrix. So this was of size 2n by 2n. This is again of size 2n by 2n. And the integral following phi of j sine j of x minus phi j of x sine I of x. This is the, I think it's the second De Bruyne formula. Now this will come in handy, right? Because if we find polynomials that have a scalar product that is orthonormal or orthogonal, which is of this sort of type, then we will be in business. So what did we do? We define the scalar product. I'm going to mention earlier. Well, I don't need to find it. I know what it is. So we define this 4 scalar products. Well, it's not a real scalar product. So let's define this with these wedges here. So this is defined by the following integral dx of f of x prime of x minus f prime of x. Okay, so if we now find our polynomials to satisfy this, okay, let me put in the weight function here so it's more consistent. So choose the polynomials that were arbitrary here. The only thing that's not arbitrary, if we choose the polynomial q, we get 2 prime. So we choose q tilde 2j and q tilde 2k plus 1 to give hj delta kj. Of course, this is antisymmetric, and then we choose for the rest 0. Q2k, 4 is 0, Q2k plus 1, Q2k plus 1. Okay. Now you can see that if we have satisfied this, then this will help us enormously applying this integral here to phi being q and psi being q prime. So we get exactly this scalar product here that will then help us to compute both the partition function and also correlation function. Okay, so
sorry,
yes,
could you please read the indices and have some information?
yeah.
For me.
Okay, so we choose the polynomial q with index 2j, so
Two,
even.
that's a two. Okay.
Yes, it's a 2. And then 2k plus 1, that is odd. So even and odd together give something non-zero when they are neighboring. So let's say 2j, so 2 and 3, or 0 and 1. And you can see that, okay, suppose they would have parity, which will turn out, then our weight function, let's say, is Gaussian. We have an even one and then an odd one prime, so that gives again something even, and then vice versa, so that has the chance to give something non-zero. Again, here again, 2j, okay, j plus 1, 2j plus 1. Okay. So now what we want to do is we want to compute the partition function. I mean, I will not do the density correlation functions. So for the partition function, okay, there's one way I could do it, but there's also a simpler way. So what was that? That was a constant integral and then we have a Wandermann 4. Now this has been replaced by this. Q tilde J Q prime, such that this is satisfied. Now, in order to apply this identity here, you see, in this identity, I don't have a weight function here, so I need to put here the weight functions. In other words, I need to pull the weights inside the determinant. And of course, you can do that giving every row and every column a factor of square root of the weight. Okay, just pulling it into rows and columns. Sorry, we will only put it into rows. Yes. And then we will apply this theorem, so then we get following results. So we get constant times. So m in our case is n. And then we get a function of this type here. So we have now weight function q, q prime. So this will always give 0 except along the first upper and the first lower diagonal when they are neighboring. Okay? And the contribution that we get is the following. We get the norms h0, h1, minus h1. Yes. And the rest is again 0. And now, if you look again at the definition of the Pfaffian, this will just give constant and order times the order j from 0 to n minus 1 h j. And these are the norms for these polynomials. I should have said so. These are called skew orthogonal polynomials. Skew because of the skew product. Okay. So we've computed the partition function now. It's again given by the product of the norms. Now I could also go about to compute the correlation functions. I will not do that, but I will rather give some examples of how these polynomials will look like. Example. Wait. Then, so this is plus, and alpha is bigger than minus 1, so that all integrals converge. And then you can find in the book, for example, the following explicit form. So if you plug these in, or this weight function, this will be satisfied. Okay. Now, as before, you can then build a kernel which is antisymmetric from these polynomials that are skew orthogonal, and then prove a theorem a la Dyson meta, now with a determinant replaced by Pfaffian. The same thing you can again compute correlation functions in this way as a Pfaffian of the kernel of these polynomials. Now, rather than doing that, I just say that in words, can give you another representation of these polynomials that is also nice. So these polynomials enjoy the following. Values. So this is the first one, and both also the other one that I give after this paper by Akemann. 0, 0, 12, 0, 46. Now, if you're not too sleepy, you should shout because this is a polynomial of degree 2j, but I've put here the j times j matrix. How does this match? This should give a polynomial of degree 2j, right? But we are at VTech with 4, so this matrix is quaternionic. So this will actually give the product from 1 to n, that's how to j, of x minus lambda j. Okay, this is because of Cramer's degeneracy. So after diagonalizing a quaternionic matrix of size j and representing the elements by 2 by 2 matrices, on the diagonal I will get blocks of this form on the I. Okay, and the product is just every eigenvalue twice. So this is a polynomial of degree 2j. The second polynomial looks, and please note, these are only the even ones. Why? Because if I put a determinant, I can only get a polynomial of degree even. Okay? So for the polynomial of degree odd, I have to do something else. And that's how I figured out how to do that. I should also say there's a paper by Panda and Gosh, which is 1 year later, which gives the same integral representation. So it's almost the same. So this will give some even power, and then we add a plus trace of h plus x, and then plus a constant size j. Now, what does that mean? Well, this means that the polynomials of degree odd are not unique. But this is not so surprising because if I add something here of even degree, because of this relation here, this will drop out always. As you see, this is just an even polynomial added to the odd one. Okay, this is just what is here, and then we drop out anyway. So it's undetermined after this constant. Typically, we choose them to be of degree. We choose the constant to 0, but we may choose it anyway. Now, for the kernel, there's another representation. Well, I didn't prepare that, but it's clear this kernel has to be odd. So I believe it's something like x minus y times the product of 2 debts. But I may be wrong, and I should check that. This is not in this paper. Okay. So this is how the program would look like for beta equals 4. Now, very briefly about beta equals 1. Somehow we are increasing the degree of difficulty. So first we had a Vandermonde to the 2, easy. First replace it by polynomials, orthogonality, done. Now here, we have a Vandermonde to the power 4. This is already more tricky, so we have to fiddle with determinants, put in polynomials and their derivative, but we can still handle that. Now, when I have beta equals to 1, I have an absolute value. That is, of course, nasty. So, what can we do with that absolute value? Well, we can order our eigenvalues, and then we can drop it, and then hope to work with that. And that's what turns out to be here. So, I think this can go. And maybe this can also go. So you see some things will repeat each other. So, beta equals 1. So let's order by eigenvalues. Lambda 1, lambda 2, lambda n. Now you remember that the Vandermonde determinant is just lambda j minus lambda I. So when they are ordered that the lambda n is the largest one, then these products will all be positive. So I can drop the absolute value. However, I have to restrict the integration, and I mean you can all do that and plot that for two variables. So just integrating over the upper triangular part will be the integral over two variables when you order them. And of course, the other one you get by changing names, and that will just give a factor of 2. Okay, so if you do that for n variables, what you will get is you will get n factorial, and then an integral over lambda 1 plus okay, lambda 1 lambda n w of product I. And now we can drop the Vandermonde determinant, and then we can replace it by determinant of monic polynomials. So let's call them again q minus 1. Okay. Now, what we have at hand for beta equals 1 is the following integral. That gives the following identity: dx1 dxn order. I mean, it's really funny because if you like, you start here with a matrix model, and then these identities that I mean, De Bruijn didn't know anything about random matrices. I mean, these integral identities fall exactly in place to solve the model. So it's really very nice. So we integrate over the determinant of phi n by n of a function phi I x j, let's say. And what we get is again a Pfaffian. And here we have to assume that n is even. Assume n even. I mean, the case n odd also exists as an integration theorem for odd n, because here, I mean, there's no difference. But I don't want to write this down because it has Pfaffian of a matrix with two more rows, one more row and one more column. Dx. Basically, you have one unintegrated then here in this division symmetric. Epsilon x minus y, phi I of x, phi j of 1. Okay, and the epsilon is just that function. So it's minus plus 1 for x larger 0, minus 1 for x less than 0, and for 0 you can define it as you like, because this is the point of measure 0. Okay. So, because of that, you think it's a good idea to define the following scalar product for beta equals 1. J1 again anti-symmetric as integrate dx dy epsilon x minus y f of x of 1. Okay. Now again you choose the polynomials to be skew orthogonal with respect to this scalar product. And then you apply De Bruijn's integration formula. You get here again something only 0 on the diagonal and h is on the upper and on the lower diagonal, and you get exactly this answer. Okay. This is how the story goes for beta equals 1. Now again you can have these polynomials uj of x represented now as 2j, and likewise for the odd ones, Again, you can define a kernel. So this will be similar. And you can again apply a variant of the theorem of Dyson and Meta for Pfaffians and show that the correlation functions for v equals 1 are all given in terms of the kernel of these skew orthogonal polynomials valid for any weight function, which I think I lost. Yes. I lost them. Okay. So this pretty much ends what I have to say for today about eigenvalue correlation functions. Now, in principle, I have a bit more prepared for tomorrow for distributions of individual eigenvalues because they are useful in the application to QCD. But in order not to lose the punchline tomorrow morning, and probably all of tomorrow's lab lecture, I will devote to explain to you why there's a limit starting from QCD as a quantum field theory, ending up at a zero-dimensional random matrix model. Now, we won't need much of this, what I have done today, but some of these ideas will be useful if you have in mind determinants, Coulomb functions, so this will come up. But so if you got a bit lost over all these polynomials, don't worry, I mean, tomorrow we'll have a fresh start. So thank you.